Hello, everybody. This is next part of our Prague seminar for mathematical physics. Today, with our kind guest Andrey Krutov, postdoctoral researcher at the Mathematical Institute at the Czech Academy of Sciences. And it's worth to be said that Andrey gave us clue that he's willing to give us his talk almost a half a year ago. So we are very glad it finally happens. And he's going to say something about Nichols algebras and quantum principal bundles. So we are happy you came to us, and the floor is yours.
Thank you very much for a kind introduction, for the possibility to present the seminar. So today I will speak about this. Yeah, so first of all, it's a joint work with Ray and Karen. It's a paper with a long history, and the recent version of it appeared finally in the last April, in this April, so a week ago or something like that. So here's a reference to R5. And it will be some talk about the non-primitive differential geometry and a bit of an algebra in braided categories. And let's start with the motivation. Yes, please. So, what is a braided manual category? So we start with some manual category. We have a collection of associated morphisms. Next, please. And then in such category, a braiding is a collection of natural transformations between functor of b functor of tensor taken tensor product and its opposite, which satisfies this hexagonal equation. And what you can think about it, well, if you're category series and everything is clear for you, what does it mean in more topological or maybe even physical terms? So suppose you have a strands and you want to braid them. So this commutative diagram basically says that if I have a three strands and I braid two of them simultaneously with one, it's the same as if I do it in two steps. So yeah. First I braid first and the second, and then I braid second. You can think also about it, so it's some topological interpretation of this equation. Another commutative diagram which reflects mirrored version should be also assumed to be satisfied. And also you can think about it as a free particles that interact pairs wisely. And in this statistics, we don't assume that it matters in which order they interacted. So, yeah. And the braided manual category is a pair of, so we have a manual category and the braiding. And next slide, please. And in this sense, consequences of the definition will be that our braiding satisfies the famous Yang-Baxter equation, one of the foundation of quantum groups, quantum integral systems, and so forth. It's more really the business what is going on behind it. And next slide is what is a simple examples of such things? I will start with very simple. So first, there is a special feature of some braided manual categories if our braiding squares to the identity morphisms. In this case, everything from my point of view will be very simple. First example, consider category of vector spaces, and the braiding is just a flip. And then this half of braiding you can define actually exterior on symmetric algebras. It will be eigenvalues because our braided manual category is symmetric. You have eigenvalues plus minus 1. So you just take the corresponding ideals and everything is. Another example is supervector spaces. Here you should put some sign into the definition of your braiding. And again, it will give you a convenient definition of corresponding symmetric and exterior algebras. Unfortunately, when you move to, for example, work of quantum groups, your category became still braided usually, but not symmetric, and you have a big problems with the definition of symmetric and exterior algebras. So one of the solution for it is Nichols algebras. Next slide, please. But to define them, I will need some notions from the theory of Hopf algebras. Let me briefly recall you what is a Hopf algebra. So here you can see axioms of associativity for an algebra. So you have two maps, multiplication and the unit map, which makes these diagrams commutes. And co-associative co-algebra is the same, but you reverse all others. So just all your notions that you know from associative algebra theory, you reverse ours, you got a notion for co-algebras. And Hopf algebra is an algebra and co-algebra plus some additional map which is called antipode, which satisfies this condition. You can think about it as a compatibility condition that in the case of the group algebra refers to existence of the inverse map for a group. Next one. So in what follows, H will usually denote some Hopf algebra. Dual notion to unit, co-unit will be defined by epsilon. Delta will refer to co-multiplication, and I will use this terrible Swiller notation that I will not just omit summation sign. I will denote my product in my tensor legs by 1 and 2. So it's just refer that we have a whole sum hidden here. It's very handy, but for the first time when you see it's very confusing. And antipode will be denoted by S. Now, so the action of associative algebra will be defined by triangles. That's this. And here is my notation for the co-actions. So in the same manner as you can draw a commutative diagrams for definition of an action of associative algebra, just reverse co-hours, you get a definition of the co-action. So you can see that now co-action goes from the co-representation to the tensor product. For example, in contrast with the right actions, you just reverse the hours, stuff like that. And here is my notation for right and left actions. So I count from my co-module to the right and to the left. And again, plus means taking the intersection with the kernel of antipode. Next slide, please. So I promise that I will give you more examples of a braided symmetric braided Manifolds categories, and one of them is a category of Yetter Drinfeld modules over Hopf algebra. So it's simultaneously module and co-module with this terrible compatibility condition. That doesn't say you anything right now, but it's here, next slide here, you require it to have the following map be a braiding in this category. So when you try to check hexagonal equation for this braiding, for this linear map, you will end up to some conditions that will look like here. So it's a motivation for this compatibility condition. So this special subcategory of modules and comodules, which satisfy this equation, is a braided Manifolds category. And we can do a lot of stuff with such things. For example, we can construct some analogs of exterior and symmetric algebras. But first, we need to define braid group. So you can think about, it's a braid group of instances generated by the following generators and relations. And if you look for a moment, you can think, okay, maybe I was planning to write a definition of symmetric group, but I forgot to write that my generator squares to identity. But no, it's how it is. So you exactly take all relations from symmetric group, but forget about the relations that your transposition squares to identities. So this group become now of infinite order. And yeah, it controls some things in topology, like this diagram that I was drawing here. It's exactly one of the sources of the definition of this group. And if you have some braided vector space, then we can construct representation of this group on the n tensor product in the following manner. So we just swap guys and each place. So you see that these generators plays a role of simple transpositions in the symmetric algebra. That's why we can define something that called Matsumoto shift. It's sections of the projections. Of course, we can quotient our braid group by the relations that all betas squares to identities, and we will get our symmetric group. There is a set theoretical section of this map projection, which satisfies the following conditions. My TIs are simple transpositions in symmetric group. And sorry, yeah. So this condition completely determines this map, and we can construct what is called quantum anti-symmetrizer. Fancy name. So it depends on it acts on the n tensor product and depends on numerator. So what we take a sum over all elements of our symmetric group, take a Matsumoto section, pull it back to the automorphism of our n tensor product, and we get this map. And so now we can define a Nichols algebra as a quotient of the tensor algebra by the kernel of all anti-symmetrizers. So we take a sum over all integers n. Okay, what is that exactly? So first, very nice Kolb algebra is just complex numbers. And very nice Yetter Drinfeld module is just a vector space endowed with this module and comodule structure. If you check Yetter Drinfeld condition, you will see that it satisfies, and the corresponding Nichols algebra will be just symmetric. Next slide. I bought a bit more sophisticated group. A Kolb algebra take a group Z2. Take the corresponding module, comodule structure on a vector space defined in the following manner. And again, it will be Yetter Drinfeld module, and the corresponding Nichols algebra is the exterior. So, but remember, this construction works for any braided monoidal category, for any braiding. So in general, we'll get something more complicated, but still we think about these examples as a motivating one. Next, please. And how they appeared. First, it was purely algebraic notion of a way how you construct new Kolb algebras. And later, it was hardly used in the classification of pointed Kolb algebras. There is a whole school around Andrushkevich. So on the paper, another source of this, I think, is differential calculus and differential non-commutative geometry initiated by Varanovich. He rediscovered Kolb algebras and Nichols algebras in slightly different concept. There is even Branislav paper about very old one. And what is the feature in this, for example, review 5? You can see that Nichols algebras allows you to bring a lot of geometrical notions, for example, contraction operators, Catan calculus, Lie derivatives to the non-commutative geometry board. But I will speak about it later. And also there is some applications of recent application of Nichols algebras in conformal field theory. I don't know much about it, but okay. Now let's move to the non-commutative differential geometry. What is a differential calculus over some arbitrary algebra? So it's some differential graded algebra which is generated in degree 0 as a differential graded algebra. So that means that our 0 form is just our algebra, and our first forms are just image of B under the our differential D. So D is a differential, that's graded rule. One of the simplest examples and one of the fundamental examples is a universal differential algebra, that the differential calculus that exists for any algebra. It's defined in the following manner. It's nice, but the problem is that it's infinite dimensional and usually it's not very useful. But next slide, please. But there is a nice theorem that any other differential calculus is a quotient of this universal construction. For example, you can think about the run calculus on the manifold, and it will fit in this construction. So your algebra, B will be an algebra of smooth functions on your manifold. Okay, next one, please. And yeah, this is construction of first order part, and we can construct also its infinite prolongation. So next. Yeah, it's how it looks like. It's purely infinite dimension. So you don't expect from some exterior algebra to be infinite dimension, but unfortunately it is. Now I want to pass to some cases of the homogeneous manifolds. So remember, when we have some homogeneous manifold, namely we have some Lie group which is acting freely on some manifold, we can leave this action to the action of our Lie group to the differential forms. Here we will dualize the picture and action become a coaction. So that's just for stating that our differential is covariant. Yeah, so it's just stating that our algebra could be thought as an algebra function on some space which is have an action of our focal algebra A. And next one. And the property of calculus to be covariant means that we can leave this action to the namely coaction here to the level of force. So again, example will be you have some G homogeneous manifold, and go back, please. Yeah, and your differential forms will be covariant with respect to the corresponding coaction. Next one, please. And one of the main objects in our studies is quantum homogeneous spaces. Remember that one of the good behaved examples of homogeneous manifolds is the quotients of Lie group by some subgroup. Now think about it in a dual picture. So let's, instead of Lie group and its subgroup, consider the algebra of functions on these groups. With a bit of work, one could endow this algebra of functions with the structure of a Hopf algebra, and your action of a group became a co-action of a Hopf algebra. So with this philosophy, that's we're reversing our errors. So this definition exactly says so. We have some big group, classically big group, which corresponds to Hopf algebra A. So it's a algebra function on it. We have some subgroup, which here will be denoted by H, and we have a Gruen map, so it's a surjective map. And thanks. If before you was considering space of invariance, here we should consider space of co-invariance. So you can think about B very roughly as a non-commutative analog of an algebra function on some homogeneous space. So quotient of some Lie group by itself. And yeah, one of the technical notion will be existence of these splitting maps which satisfy certain condition. And yeah, next slide. If our initial algebra was Hopf algebra was co-semi-simple, namely its category of its co-representation is co-semi-simple, semi-simple, which means that everything splits in the direct sum of simple objects. Okay, now I will need some, we'll try to explain what is the analogs of principal bundles, so quantum principal bundles. First, it will be some universal construction that is actually very handy in algebraic world, but so what is a Hopf-Goulart extension? Then we have some algebra is a co-action of so we have an algebra P with a right co-action of Hopf algebra H, such that multiplication map is a homomorphism of homogeneous. Then a Hopf-Gola extension is defined in the following, by the following condition. Next slide, please. It's equivalent to existence of this short exact the following exact sequence. It could look a bit strange, but if you will think about principal bundles, you can split your differential form into horizontal and vertical one. So here, this guy will be your vertical forms. Oh, sorry, horizontal forms. This guy will be your analog of your vertical forms. And you see, we use this notion of the universal calculi. So such thing always exists because universal calculi always exists. This construction is very nice from algebraic point of view, but from the point of view of studying geometry, it's not very handy. Next one. So one of the examples, for example, consider a group algebra. The Hopf algebra structure is defined as follows. Next one. Then, if you have a G-graded algebra, then it's a Hopf-Gola extension if it's a strongly graded. And you can see this. So if you take two guys that squares to identity, when we multiply them, we should go. Yeah, it should be E here, sorry. Sorry for it. Another example will be principal bundle over some G manifold. Next one. So here is just for a set. You can see Hopf-Gola extension. I'm not really using now a manifold structure because in the definition we have a universal calculi which doesn't reflect any geometry. So that means that I would consider it for a set with a free G action, and by purely I denote algebra functions of my objects. My algebra function in a set, for example, if it's a finite set, then it's just a collection of copies of complex numbers. Okay, great. Now, to give a bit more differential geometrical taste to this notion, Brzezinski and Majid introduced the notion of a quantum principal bundle. So we start with now not with a universal calculus, but with a given calculus over our algebra. And it should satisfy some additional requirements. Okay, thanks. Next one. And again, this definition implies a similar decomposition of our forms into horizontal part and vertical part. And for example, the run forms, differential forms on the manifold will fit this picture. Okay, nice. So now in this slide, I will try to explain you the notion of induced representation. Let me recall you that if you have a homogeneous manifold of the form G mod P, so G and P, for example, parabolic subgroup of unit. Then, starting from the representation of P, you can construct a corresponding homogeneous vector bundle. You start with the representation P, it gives you a homogeneous vector bundle. The same principle will work here. Just for some time to for people. Okay. Now I will explain how to use this construction to go from some, in the case of quantum homogeneous space, to go from the co-module of a group to the corresponding homogeneous vector bundle. So let's start with the category of H comodules, and the second category is defined as follows. You can think about these guys commutatively as a sections of homogeneous vector bundles. So they have a bimodal structure. Remember that classically you can multiply sections of any vector bundle by a smooth function on the base. And then existence of this H coadjuvant refers to the fact that they are homogeneous. And there is an equivalence between these categories. I will hide a bit of details on the card, but you can always read the preprint. The fact that we have a joint equivalence, so we can switch from co-representations to homogeneous vector bundles in very easy manner. And that means that we also could think about the, if we start with the sections with some homogeneous vector bundle, and we want look over its fibers, so we want to look at locally. So then we can use this functor to transfer to the local category and look at the corresponding co-representation. So co-representations are vector spaces with some additional structure, so it's needed sometimes. It will be one of the points in my talk. So you can think about this, this functor as going from a global picture to the local, and this functor goes into the direction. Next one. And yeah. Okay, this homogeneous covariant calculus are very nice, but you often meet a lot of problems. For example, you can construct, for example, first order calculi. You know how your first order forms of degree 1 behave. You know the differential that goes from your algebra to degree 1 forms. But usually you have a question how I could construct higher dimensional form, higher degree forms. And it's usually very tricky for just left covariant. If you have a bicovariant calculus, so it's bicovariant from left and right, there is a nice theorem proved by Varanovich and some algebraists independently that if you have such a calculus, first order calculus, you have an object in you have a Yetter Drinfeld model structure, and then you can extend your first degree forms to higher order degree forms just by construction of a Nichols object. What is it? So everything is nice, but yeah, could you go back, please? Yeah. What's the problem here in the case of, for example, quantum groups? Unfortunately, well, first of all, motivation for bicovariant calculus, if you consider the round forms on your Lie group, they will have bicovariant. Yeah. You can multiply by from left to right, for example, by the action induced left and right constructions. If you will pass to the notion of a quantum group, yeah, you can construct such examples, but your calculus will have a non-classical dimension. For example, consider the simplest case of SU2. So it's three-dimensional manifold. So your first order differential forms locally should look like a three-dimensional vector space. In a quantum case, it will be unfortunately four-dimensional. And it holds for all quantum groups. So that's why it's not very handy. And approximately, I don't know, 20 years ago, the bicovariant approach to differential geometry was a bit abandoned. That's why it's a bit surprising that we recover things in the different contexts.
Isn't that in the jar?
Homogeneous manifold. Of course, we cannot speak about bicovariant calculus since we already quotient one of the covariants when we took homogeneous, when the test is a homogeneous space, so they will also have only right and or left coaction. But it looks like that if you have a quantum principal bundle over homogeneous space, which satisfies some very natural technical conditions that I don't recall here, I refer to the paper, then we consider the corresponding calculus on the base and consider the corresponding cotangent, quantum cotangent space. And so miraculously, we can define a Yetter Drinfeld model structure on this cotangent. So we can speak now about Yetter Drinfeld structure. So again, we started with something which is not supposed to be in that category. So because it's not bicovariant, it will be only left. But yeah, we got this Yetter Drinfeld model structure picture, and it's the main theoretical result of the paper. And now I will go to nice important example. Okay, next one. So back more to the ground. So I will speak about quantum flat manifolds. I will start with the Drinfeld-Jimbo quantum groups. We start. It's a deformations of a universal enveloping algebra of simple complex finite dimensional algebras. So we have a Cartan matrix. We take a parameter Q and we consider this algebra generated by these elements. So E and F, as you can imagine, corresponds to the corresponding Chevalier generators in the universal enveloping algebra of G. And K corresponds to H's. Well, morally, it's K, you can think about it as exponent of H bar times H, when H is your Gassian Cartan selection. And we have a deformation of a multiplication here, analog of quantum serial relations. So formulas look horrible, but at least it generalizes you if you remember relations for universal enveloping algebras, and you recognize some of them. And it's a, and next slide, and it's a whole algebra structure. One of the things that really matters here is that look at the definition of a co-multiplication. In the case of just universal enveloping algebra, instead of Ki here and Ki inverse, you will have 1. And more or less, it's the fact, if you refer to the fact that the category of representations is a symmetric Manifolds category, because when you square, it will be identical. Simple and unfortunately, it will be not the case for the category of representation of quantum. Next slide. What is good? This Jimbo gas has a very nice category theory. Basically, it's more or less the same as a representation theory for the corresponding Lie algebra. So at least for finite dimensional guys, they indexed by the integral dominant weights. You have notion of a irreducible model with the highest weight. So all your positive guys kill the corresponding highest weight vector. K's act as H's, so they act diagonally. You can recognize formulas from your Lie algebra course. And we'll denote the category of such representation that type 1 guys. And yeah, next slide. Of course, it's all fit in the weight theory. So there exists one nice subcategory of category of representation of the quantum group, which equivalent to the category of finite dimensional representation of a corresponding Lie algebra. There is much more structures, but I don't want to go into details. If you want, you can ask questions later. Next one, that we will use this part to define analogs of quantized coordinate algebras. So first, let's speak about the matrix coefficients of our representations, which is defined in the following way. And so the coordinate ring of your representation, yeah, you can remember this formula, for example, when you study representations of simple associative algebra. And in the case of Lie groups, we have a Peter-Weyl decomposition. So that the algebra functions decompose into direct sum of coordinate subalgebra, coordinate algebras of representation. In this mimicking this construction, we define quantized coordinate algebra. Yeah, that's fine. In the following manner. So we take all coordinate rings for all finite dimensional type 1 representation of the corresponding D2G for quantum group. Next slide, please. And yeah, it will be cosine simple as you can expect, and it will matter later. Let's go to the flat manifolds. So they could be constructed from the same data as a classical one. We take a Dynkin diagram of our Lie algebra, put some crosses on nodes, and construct the corresponding Levy subalgebra in the following manner. So, and then with a bit of a magic, we can construct the corresponding surjective algebra map, which will give a structure of a homogeneous vector space. If you will do it just for universal enveloping algebra of G itself, you will end up with the algebra function on the corresponding classical flat manifold. So just a direct generalization slide. And yeah, the corresponding quantum homogeneous space will be called quantum flat manifold associated to the choose of cross nodes S. So this is space of invariants. Yeah. Next one, classically, yeah, now there is a very nice subclass of quantum flat manifolds, which is called the reducible one. They classified in the following tables. So it's, for example, Grassmannians, the first line that we will be interested in. So you can take one cross, whatever you want. For example, if you will take a cross on the last or the first node, you will get projection spaces. If you take just one node, cross it, you will get a sphere. So again, it's classified by the same data as a classical one. So I could really remove the quantum word here. But why these guys very special in the quantum world? Next slide, please. Because for them exists very nice differential calculus. By very nice, what I mean? I mean that it's covariant. So we have a coaction of our big quantized Lie group over it, OQG, and also it has classical dimension. So in contrast with, for example, calculus on quantum group itself on OQG. So, very nicely. So it was discovered by Heckenberger Kolb, and it possesses a decomposition, so more generally it has some complex structure, but here, what is more important, the first order, the first degree form could be decomposed into homogeneous parts. There's two sub-objects in this category, the global category. You can think about them as a holomorphic and anti-holomorphic forms. Next one. Now, yeah, I was speaking a lot about generalization over exterior and symmetric algebra. So in the next, I will be more focused on exterior guys. And one of the facts, so this category is braided modular category. But whereas the braiding constructed in the following manner, so you have some elements that are called universal L matrix, and for true representation, braiding is defined in the following manner. Tau is just a flip. Yeah, but the problem is that this category of representation is not symmetric. So eigenvalues of braiding will be of the form plus minus q to some power. So you couldn't pass to the natural definition of a symmetric algebra or exterior algebra as an eigenvalues plus minus 1. But another problem, if you will consider the corresponding Nichols algebras, they usually will be too big. So for example, your analog of exterior algebra will be infinite dimension, which we don't want to do. There is one solution that was proposed by Nichols following ideas of Drinfeld on his study of braided quasi-Kolb algebras. We can normalize our braiding in a following manner, some horrible formula. Next one. What is the feature of this normalized braiding? That eigenvalues of this guy will be just plus and minus 1. And this is recipe that works only for this braided Manifolds category. Why it's bad? It doesn't satisfy Young-Baxter, and the corresponding algebraic structure is much weaker. But then we can define this quantum symmetric and exterior algebra in a usual way. Consider these two ideals in the tensor product of module with itself and quotient. Yeah. The problem with this approach is that it will give you classical dimension of the exterior algebra only in some cases. And there is a nice theory behind it that corresponds to the existing of some solutions of Young-Baxter equation classically as some R matrices, but I don't want to go to the details. What is more important is that for irreducible Flank manifolds, this cotangent, if you look at the corresponding guys here, so they will holomorphic and anti-holomorphic part of our calculus, they will be quantum exterior algebras. Okay, so it was a bit of a digression. Now we can consider some quantum principal bundle over our quantum Grassmannians. So the first line in our story. Unfortunately, from this picture, we couldn't recover Heckenberger and Kolb calculi. So already here we are in the situation when we could apply our main technical result and construct some Yetter Drinfeld module for this calculi. But it turns out that this picture that you want to that naturally to consider first is not relevant. But Alessandro, Colin, and Trey proved recently that there is a nicer principal bundle picture for the quantum Grassmannians such that the corresponding restricted calculi correspond to a Heckenberger and Kolb calculi that have very nice properties. That means, and moreover, it satisfies technical conditions that we require for our main theorem. So next slide, please. And it's another main result of the paper that by applying our theorem, we can define a Yetter Drinfeld model structure on a cotangent space of Heckenberger and Kolb calculi, and moreover prove that holomorphic and anti-holomorphic forms will constitute Nichols algebras. How much time do I have? Oh, 50. It's going too fast. Then let me give you a clue how to prove this fact. It's probably will give a light of more technical details. So if you look at the first order forms and apply our functor phi locally as a vector space, it has a very nice basis. And our calculi has, so our quantum exterior algebra have this set of relations. So you see that it sometimes commute, sometimes commute up to q with some power, but some relations are very good. Yeah, next slide. Yeah, so just a bit of facts that our cotangent plane cotangent part of the calculus splits into two dual modules with respect to this quantum group. Next one. And we can explicitly write it in terms of a highest weight. This box tensor product means that I take a representation of SLR and then tensor it with a representation of GLN, because I will use a lot of tensor products. So when I take a tensor product of it, it will split into two parts. It's a direct sum of irreducible UQ G modules, and if you consider to compute the corresponding quantum stereo algebras very carefully, then on the first line it will be submodules that correspond to the symmetric algebra and the guys that correspond to exterior algebra. Moreover, the whole, as I mentioned, the anti-holomorphic forms is, when you look at them locally, look like the corresponding quantum stereo algebra. Just following the definition. Next time. And because of the Manifolds theorem, we also know that since we have on V, we have a structure of Yetter Drinfeld module, we can construct the corresponding Nichols algebra. Next one. And direct calculations show that at least in degree 2, these two ideals coincide. So that means that our Nichols algebra is a quotient of quantum exterior. And let me be the corresponding projection. Now let's go a bit into details how it works in degree 2. We can decompose this tensor product of V with itself into irreducible components. We'll have this set of highest weight vectors that correspond to irreducible guys, irreducible submodules. Next one. Then we can construct Yetter Drinfeld braiding and act on these guys. So this, for example, why you could say me, okay, but you already told us that without your result of quantum principal bundle, the category of representation of your Drinfeld quantum group is a braided model category, so we have some grading given by parameters. Yes, but in this case, the eigenvalue of this grading will behave very bad. For example, see, here to give a nice dimension of the corresponding Nichols algebra that will be the same as classical exterior algebra, we should kill module with the highest weight V1 and V4, and our grading do the job. Because remember, quantum anti-symmetrizer in V2 looks as follows. You take a kernel of identity minus grading. Exactly. These two guys will be used. But unfortunately, for aeromatic grading, we will not have the same results. These two eigenvalues are different. And no. You go back. But it's another explanation why this Bernstein-Zitsnagel approach works. Remember, I was telling you that Bernstein-Zitsnagel, what they do, they normalize grading. So they forget about any scalars here. They just say you, okay, if your aromatic grading was given as something positive, then our normalized grading will multiply by 1. If it was something negative, then it will multiply by -1. Next one. And now we know that our quantum theory algebra was finite dimensional, so our Nichols algebra is a quotient of it. So it's also finite dimensional. That's K, you know, the dimension. For Nichols algebras, we have a nice quantum graduality, which means that it's very symmetrical in components dimension. And referring to the quantum version of a skew Hall duality, we can see that our whole quantum theory algebras could be decomposed in the following manner. What is more important here? that in this decomposition, we will have exactly two trivial one-dimensional modules. One in degree 0 and one at the top degree. Excellent. Yeah. And we know that the same should happen for a Nichols algebra. So we know that in exterior algebra, we have two one-dimensional guys, the top forms and the zero form. The same holds for Nichols algebras because of the regularity. So the top forms pass through our form. So the dimension, the top grading degree of top forms.
No, I was actually just while listening to the seminar, so I could actually.
Now there's a result by Ulrich Hammer and Simon Machaga that it's a Homogeneous algebra, the quantum stereo one, and where corresponding bilinear form is actually given by some Berezin type integrals. We should take a multiplication of two forms, and if you get something of the maximal degree, then you just take a coefficient. And you can either deduce that from existence of this bilinear form, you can get to the contradiction. So remember that I is our ideal, so we assume that our Nichols algebra is a quotient of a quantum exterior algebra by I. Looks like this. And we can see that our ideal is 0, so they coincide.
Thank you very much for a nice talk. So, please, if you have any questions, remarks.
Why is it important? That the cotangent space must be equal to the reference HK1.
Yeah, okay.
This is my definition.
It's good to have this Nichols description of the calculi by the following reason. The whole of this business with non-commutative differential calculus appeared 30 years ago. They were studying bicovariant calculus, and in bicovariant calculus, you have a built-in notion of a Nichols algebra, corresponding Nichols algebra. And using this notion, you define contraction operators, D derivatives, corresponding Cartan calculus, Bianchi identities. So a lot of things that you have in the classical differential geometry. The problem is that you don't have a now, when we pass through the quantum manifold, we have a calculus of a nice dimension, but to define contraction or Lie derivative of this get, it's a bit of an issue. Because, okay, even if you have we know that they're quantum exterior algebras, there is not so many tools how we can study them or we can handle them. So that's why it's very surprising that we have a description of in terms of Nichols algebra, so we can use this machinery now.
I would have maybe one very low-brow question, because a bit lost at the very beginning when you defined the universal construction of the calculus. How does it work? Or
Could you go back to slides?
Yeah. Slides.
Yeah, makes sense. Yeah, it should be. You mean the just
how you define the universal calculus from which you derive all the calculus by factorizing or quotienting?
Yes, one step back. Couple of slides back, but we are close. Yeah, one more.
Yeah.
You define the first order forms as a and you define the differential that is called.
What's the differential actually? This is defined as this way, and then the hardest part is to show it really produces the calculus.
Yeah, then to define the high order forms, you need your zero form and your higher forms.
Okay.
And then, yeah, with a bit of a trick, I could show you later you can extend the differential to the higher order forms, and then you prove that it's actually differential. So it starts to zero, and so it stays like
Okay.
But it's generally related. Something can find change.
It's very handy. Okay. Any other question?
So you can now develop the notion of connections.
Yes. Even
so you have like an idea.
Yes.
At some point, we wish to find an intersection with work of ours, because we had a talk about the construction for a higher kind of connection, differentiable bundle, but it's only classical manifolds involved. So combination of your work would be nice at some point.
Yeah. Also, there is also this calculus appears not even in context of commutative geometry. I think it's Yeversky then to describe some BV type series. I don't remember exact reference. Yeah, Vasily and Yeversky. Yeah, there is kind of different application of this case from unexpected point of view. They was defining algebraic type structures. So there's a the algebroid is a super manifold and a homological vector field that squares to zero. And they was doing something like that for some reason. Not an expert, unfortunately. Yeah, but yeah, it could probably be useful.
So
very nice.
What doesn't work in case of the more general manifolds?
Because we don't know yet the calculus. So Ray and Petter know probably for some of them, or it should work, but we don't have this Heckenberger Kolb calculi yet.
They could structure the calculus just to be reducible, and the question of the extent hasn't been looked at. Petter was not for so we've done for the A series, but we haven't written it yet.
I mean, this is kind of something very different. This calculus as the one you get just restricting the calculus on the proof.
It's if you take the covariant like discovered, then you're going to get something much higher dimension.
Yeah, even after
Well, if you quotient out,
if you quotient out,
then you get it.
Then you get it.
On which page?
Probably here.
Oh, I see.
Well, that should be the other series as well.
Yeah, because kind of the representation
There's something strange going on with the reason that
I think
you can see it in the proportionary. So we can figure out what the correct way over
Yeah. Actually. Yeah. So when you start with a bicovariant, it's much stupid.
Yeah, okay.
You should take a course. And one of the important things that look like bicovariant is not so well. The important figures. What you really should look is you should look at the, for example, G covariant from one side and H covariant from another side. So, and if, it's already more or less built in the definition in the results of Magic, right? There is also some relation with corresponding Yetter Drinfeld HA modules. It's written in the paper, but yeah. So we should consider some finer structures, some substructures in the bicovariant column.
I guess an important point is that the quotient measure
you have a calculus that corresponds to each manifold.
One of the ideas of understanding the shape all of the flags well enough, and especially when the flag is just a torus. Yeah. I
think we have a disagreement here. I think it's, in FRT papers, it says that the quantum worlds separate cases. So now instead of one object, you have a family of objects. So for every flag manifold, you have a calculi, which is subobject on the equivariant, and
and maybe at this point I should stop the recording.
Thank you.
How can I stop it? Sorry for this.